Hello, my name is Simon Horman. I am the Chief Scientist of SmartNICs at Corigine, and today I'd like to talk about hardware offload of QoS for OVS. So in this presentation, I'll be covering some recent work in this area, and two topics in particular: packet per second rate limiting, and the modeling of open flow meters using the police action. Firstly, let's start with packet per second rate limiting. So OVS has a number of features for QoS, and perhaps the oldest is the port-based rate limiting. It applies a limit to packets received on an OVS port. This limit is in bits per second, and it has a burst. Over limit packets are dropped. So in this way, someone can configure a system whereby a limit, in this case 1 megabit per second, is applied to packets received, for example from a virtual machine, and packets that exceed that limit are simply dropped. In the past years, a hardware offload facility has been added for this, and this leverages the fact that when using the kernel datapath, the implementation of this is via the TC filter and the police action. So in this example is in TC speak, the same as the previous example given in OVS speak. And here we apply a rate of 1 megabit per second. And the burst number is different. That's because there's a multiplier of 8 involved. But nonetheless, this is the same as the previous example. So now we get to the slightly newer work, which has been done by Corigine over the past year. So we had a need to supply a packet per second rate limiting as opposed to bit per second. So from our point of view, the way to do this was logically to extend the police action to allow it to run in a different mode, whereby instead of applying the limit based on bits per second, it was based on packets per second. So here we have example in TC of this being used. So here we have 2000 packet per second rate limit with a burst of 400 packets. Now each police action may only run in one of the two modes at a time. It either may apply a packet per second rate limit or a bit per second rate limit. In order to combine them, one can just simply chain police actions, and that is the case here. So any packets that are over limit for the packet per second rate limit are dropped. Those that are not dropped proceed to the bit per second rate limit. Any that are over limit at that point are dropped, and those that are not over limit may continue. Here we can see that, same as the previous example, has been translated back to OVS configuration. So we've extended the OVSDB interface to allow these two new parameters, the kilopacket per second rate and the kilopacket per second burst. And we have also configured a bit per second limit, the same as the previous example. So the hardware offload interface for this inside the kernel looks a bit like this. There's an API called the flow rule API, and it encodes each of the supported actions, in this case the police action. And we extended this API by adding two new fields, the burst packets per second and the rate packets per second. You can see existing burst and rate byte PS fields, which relate to the bit per second rate limit. So each offload driver may choose to implement this or not. And I believe at this point only the NFP driver, which is the driver for the Corigine SmartNICs, supports this feature. So by supporting the feature, what I mean is the NFP driver will accept configuration of this offload, whereas all other drivers will reject. So what is the status of this feature, the packet per second rate limiting? On the kernel side, the enhancements to the TC police action were accepted into the 5.13 kernel. The police action itself was modified. The flow rule API was modified, as I highlighted, and we also added support to the NFP driver. For OVS, the support for the feature was added to the 2.16 release of OVS, and as I mentioned before, it's configured via OVSDB. So let's move along to meters and how they might be modeled using the TC police action. So firstly, let's take a look at OpenFlow meters. What kind of properties do they have? Well, they're N-band meters. Each band has a target rate, which might be in bytes per second or packets per second. Packets that are over limit may be dropped or marked. They're independent of flows, which is to say that meters are created and destroyed independent of flows, and when they're created, or after one has been created, it may be used by one or more flows or zero flows. Also independent of ports, so each flow belongs to a port in a sense, but flows that belong to different ports may use the same meter. So these last two properties mean that meter may span multiple ports and multiple flows. Looking at an example of this, a hypothetical example. So here we have a meter, number 99, we're creating it. It works on kilobits per second. It has a burst. Over limit packets are dropped. The rate is 1000 kilobits per second, 1 megabit per second. It has a burst of 100. We then apply this meter to each of two OVS ports, dev1 and dev2. And for each of those ports, we create a flow. If a packet matches either IP or IPv6, then the meter is applied, and the packet is then output to a third OVS port, dev3. So in this way, this meter, number 99, is applied to 4 flows, 2 flows belonging to each of 2 OVS ports. So this rate limit of 1 megabit per second is applied to different flows on different ports. Now let us consider OpenFlow meters and the TC police action. A TC police action instance is single band. However, multiple bands may be created using multiple action instances. It's also worth noting that for the use case we have in mind, we only require a single band. So this is not considered to be a problem. Each instance of a police action has a target rate. As covered earlier in the presentation, this may be in bits per second or now packets per second. Packets that are over limit may be marked with the assistance of another action or dropped by the police action itself. Police action may be independent of filters, and it may be independent of net diffs. Overall, we see that this is a remarkably close match between the features of OpenFlow meters. And for the subset of OpenFlow metering that we're interested in offloading at Corigine, it is an exact match. Now let us revisit the previous example, this time expressed as TC rules rather than OpenFlow rules. Firstly, we create the police action instance, index number 99. It has a limit of 1 megabit per second and a burst of 100,000. Then for each of 2 net devs, dev1 and dev2, we add 2 filters, one for IP protocol and one for IPv6. Each of these filters uses the police action instance. So for the 4 filters that are created, all of them pass through the same meter. And that is that 2 flows on each of 2 NetDevs share the same meter. This differs slightly from the previous OpenFlow example in that the output action is not included, but this can be added to these rules. Now let's move to hardware offload of meters. We have implemented this using the flow rule API, which is mentioned earlier in the presentation, and we've done this by adding a new top-level object, the setup action. This is a first-class citizen, along with other types, such as that to instantiate U32 or flower classifiers, or blocks. Blocks being an abstraction that are used to allow the replay of existing offloads in the system when offload devices are added. For example, when the driver for an offload NIC is insmoded. We then hook into the existing class and act APIs in order to make calls to the flow rule API on creation and modification, deletion, and statistics. TC actions have statistics. These are not typically used by OVS. However, we implement this for completeness of the TC API. What is the status of this work? For the kernel, we have posted patch sets to implement these features. We are targeting inclusion in the 5.17 kernel. This includes modification to the class and action API, which form part of the TC subsystem in the Linux kernel, the flow rule offload API, and we will follow up with patches for the NFP driver in order to allow hardware offload of this feature. For OVS, we have also posted a preliminary RFC patch set, and we are targeting inclusion in 2.17 pending progress of the kernel upstreaming process. That concludes my presentation on hardware offload of OVS QoS. Thank you very much for your time.
Right. Thank you, Simon. Good to see you. It's been a while. Thank you for the talk, and thank you for the work behind the talk. Let's see. It looks like we have a couple of questions already. So let's see what we have here. The first question is from Marcel Leitner, who says, as the NFV driver can offload only the flower classifier, can vSwitch use it instead of the match all filter now?
Yeah, right. So the NFP driver does offload the flower classifier, and that is the bulk of the offload facility it offers in this area. But in this particular case, we do actually offload the police action attached to the match all filter. I don't actually think we offload police are attached to flower. It's not really a limitation of the driver or the hardware. It's just that we offload what is required for the OVS use cases. That's kind of how we scope things. And then we can extend them later if the need arises.
Got it. So let's see. We're out of the questions that have been submitted in the chat. So what I often ask is, once you've got this, what are your plans for the future? What would be the next thing to work on?
Yeah, this one has taken a little while. I seem to get involved in things that take a while. Yeah, I'm not sure that for rate limiting, we have a whole lot more we'd like to do. There is, of course, there's 3 main facilities for QoS in OVS. There's metering, which we discussed. There's the port-based rate limiting, which was also discussed earlier in the presentation. But then there's also the egress shaping facility, which sometimes called set queue, because as the OVS flows set queue, and the queue is where the shaper is. I suppose that one might do some more work on that, and in fact we have done work on the past, but I feel for the use cases that we're encountering at this time, and others' experiences might be different, that actually what I covered in the presentation actually fills in most of the gaps we're seeing with regards to users' requests for these kind of features.
I see. Well, I'm sure that that something will crop up after this is in. That's the way the world works. I've never met a software program that was really complete. And when you start combining software with hardware, I'm sure it gets even more exciting.
Oh yes, that is true.
We have a couple extra minutes. If there's anything you want to add, then we have time for that.
Yeah, I'm sorry, not a lot. It's actually kind of late in the day here.
Oh well, I'm sorry for keeping you up.
No, not that late, but I should have prepared a few more points. I also apologize for the lighting. I didn't realize it would be so dark. What can I say?
I've seen worse. Well, yeah. There's no reason to press you to fill in. But thank you again for the presentation and for the work behind it. And we can move on to the next talk then.